So let's take exactly where we left off yesterday with a few examples. So these are examples involving limits involving trig functions, okay? So evaluate the following limits. Okay, so start over number one. So right away, I'm going to go to something a bit harder. So limit as x approaches 0 of, let's say, sine x over sine 3x. Okay, so remember from yesterday, we proved, okay, that the limit as x approaches 0 of the sine of x over x is equal to 1. Okay, so this is given to us now that we're going to use, and we proved it last class. Okay, so how are we going to do this one here? So now I have a little problem because I don't see any x. I see sine x over sine 3x, and I don't see any sine x over x. So any suggestion?
Yesterday we wrote down like some of the formulas, and we wrote down if sine of 2x is also equal to 2 times sine x times cos x. So yeah, maybe we could put that in the bottom and then work something out.
No, but the bottom is sine 3x.
Oh, well, instead of 2x, put 3x. So 3 times sine x times cos x.
No, that doesn't work. Who says you could do that? No, that doesn't work. Okay, it's a good attempt. It's a good reflex, and there's a way, for sure, there's a way to open this in terms of sine x and cos x. You're right, but it's not gonna. You don't just pull out 3 and put cos next to it. It doesn't work. Okay, we could do if we were in grade 11, I would push further into that, but it's not in the scope of this course. Okay, so I need to have this form here. Okay, so first of all, as usual, okay, I replace the x by 0, so sine of 0 is 0, and at the bottom sine of 0 is 0. So I have 0 over 0. Okay, so always check this. Don't forget to check this. So what I'm going to do is as follows. So sine x over sine 3x, and I'm going to divide the top and the bottom by x. Divided by x and divided by x. Okay, top and bottom. Okay, so what's the purpose of this? It's because now I could write something like this. X approaches 0, a big bar. So on top I have sine x over x. And on the bottom I have sine 3x over x. Do you get it? Okay, I divided the top and the bottom by x. I'm allowed, right? As long as what I do on top I know the bottom, I'm allowed. Okay, so now equals, and now the limit I could put everywhere I want. So it's limit x approaches 0 of sine x over x at the top, and the bottom, limit x approaches 0 of sine 3x over x. Okay, so now I end up with 2 limits to evaluate. The top limit and the bottom limit. Okay. The top limit I think is very simple. Of course, it's 1, right? It's 1. X approaches 0 of sine x over x is 1. So the top is 1. And the bottom I have to do a bit of work, but this is nothing new for us. Okay, I think we're good at this. So I'm just going to multiply by 3 on the bottom and 3 on the top, right? We've done this. And so I have on top it's 1. And on the bottom, I'm going to pull out the 3. 3 times the limit as x approaches 0 of sine 3x over 3x, which is also 1. Okay, and so my answer is 1/3. Is this clear? Okay, you will try one? So try one yourself. I'm going to split the page in two, and I'm going to do another one right here. Okay, so you have it in front of you. So let's go like this. Okay, so example 2. Okay, limit as x approaches 0, let's say sine squared of 2x divided by sine squared of 5x. Okay, so the first thing we do, we plug in 0. So I get sine squared of 0 is 0, sine squared of 0 is 0. So again, and then I will do equals to limit as x approaches 0 of sine squared of 2x over sine squared of 5x. And of course, I'm going to divide again by what? Top and bottom, we divide by what?
X.
Nope. Not by x.
Highest power.
Okay. Oh, I received a picture, so it works, guys. If you want to send me pictures so I could see your work, that works. Okay. Perfect. Yeah. So what you did is good. Okay, Amanda, you send me pictures. Nice. Okay. So I'm going to divide by x2. Okay. Because now I can go like this. Limit x approaches 0 of sine squared of 2x over x2 divided by sine squared of 5x over x2. Okay, you following? And now I could do, this is 2 problems, 2 independent problems. Okay, so the top will be sine 2x over x squared, and the bottom will be sine 5x over x squared. Okay, and so I'm going to put the limit inside each of them. So equals to the top, I'm going to get limit x approaches 0, so sine 2x over x squared, and on the bottom, limit x approaches 0, sine 5x over x squared, and I'm going to multiply here by 5, and the top by 5, and here I'm going to multiply by 2, and the top by 2. Okay, just like we did yesterday, I think. Okay. Oh, sorry, you couldn't see the bottom. Okay, and now I'm going to extract the 2 outside the limit and then outside the square is going to become 4. And on the bottom, I'm going to extract the 5 out of the limit and out of the square. It's going to become 25. And that's it. I'm left with limit x approaches 0, sine 2x over 2x, all this squared. And at the bottom, limit x approaches 0, sine 5x over 5x squared. Okay, so this here is 1, and this here is 1. So that's why my answer is 4/25. Okay, so most of you guys got it right. Okay, so Gabriela, I got your work, and it's wrong. Okay, you can't do this. This is wrong. Okay, so sine 2x is not the same thing as 2 sine x. That's not the same thing. You can't pull out the 2 out of the sine, and same thing with the 5. You can't pull out 5 out of the 5 from the 5x. You can't pull it out of the sine. You're not allowed to do this. Okay.
I have a question.
Yes.
Where does the 4 comes from?
Excuse me.
Where does the 4 come from?
Which 4?
The 4 on 25.
This one here.
Yeah.
It's because when it's this 2, okay? So this 2 here, I'm going to pull it out of the limit, it's here. And then I'm going to pull it out of the brackets, so it becomes squared. It becomes 4. When you take it out of the bracket, you have to apply the power 2 on it.
Okay, and the square, the cubes, no. Like
What?
the power 2 stays there?
Which power 2? This one here?
Down.
Down? Here?
Yeah, this one, yeah.
Of course it stays, why not? It doesn't disappear.
Okay.
What happens is that this, what's inside is 1. This we know it's 1 now. And 1 power 2 is 1.
Okay.
You understand?
Yeah.
You sure?
Yes.
Okay. Okay, let me see.
Sir, I have a question.
Yes?
So right at the beginning, I took out the square, like before you divided them by x. I don't know if I'm supposed to do that, but I got the same answer.
Yeah, I did the same thing.
What did you do? You pull out a square? Or
I
you took the
pulled-
square outside everything?
Yeah.
Yeah, so I put
Yeah,
the
that's
whole
good.
thing in brackets squared.
That's good too. Yeah.
Okay.
Okay. So I got a, 1 second. Okay, any questions? Okay, let's go with one that's a little bit harder. Number 3. So look at this one. Limit as x approaches 0 of 1 minus cosine of 2x divided by sine squared of 3x. Okay, do you want to try it? Or you want me to do the first one like this? If you have no idea how to do it, I will do it. If not, I will let you try it. What do you prefer? You want to try it? Okay. So go ahead, I want to wait. Okay, so the first thing we do again, we plug in the 0 inside. So cos of 0 is 1. 1 minus 1 is 0 on top. And on the bottom, sine of 0 is 0. Okay. So let's go. So what did you do? I'm curious to see what you did. Any suggestions? No, the one? Okay, so nobody's trying. I don't know, you got it right though. So I will multiply by the conjugate here. 1 plus cos of 2x, and the bottom 1 plus cos of 2x. Okay, so this is a very common pattern that you will recognize when you see 1 minus cos or 1 minus sine. It's very practical to multiply by 1 plus cos or 1 plus sine, because this is what happens. So 1 times 1 is 1. 1 times cos, so it's plus cos 2x, minus cos times 1 is minus cos 2x, and minus cos times plus cos is minus cos squared of 2x. That's what I have on top. And then on the bottom, sine squared 3x times 1 plus cos 2x.
I
Okay,
have a question.
yeah.
So does the 1 minus cos 2x, and like it doesn't equal cos squared x minus sine squared x, right? Because the 1 is attached to the.
Yeah,
Okay.
exactly. Okay, so I'm going to cross out the cos 2x. Okay, and then equals limit x approaches 0. So on top I have 1 minus cos squared of 2x over sine squared of 2x times 1 plus cos of 2x. Until here, do you have any questions?
I have a question.
Sure, go ahead.
Where is it 1 plus cos 2x?
Why is it that?
Yeah.
I decided to multiply by that, right? This is my decision that I added this here. This top and bottom multiplying by 1 plus 2x, cos 2x. Why did I do this? Because I noticed that when I'm going to multiply them, all the cos 2x will disappear, and I'll be left with 1 minus cos squared. And that's a very known identity. Okay, I don't know if you know it. You know what this is equal to? 1 minus cos squared.
Sine square x.
Yeah, this is sine squared x, okay? Because if you remember, we showed when we were reviewing trigonometry that sine squared x plus cos squared x is equal to 1. So if I send the cosine on the right side, the cos squared, so I'm going to get sine squared x is 1 minus cos squared x. Okay, so basically here I have 1 minus cos squared, so this is equal to sine squared. The top is equal to sine squared. Okay, so let me write this.
Sir, you wrote sine squared 2x instead of sine squared 3x.
Thank you. Great. Okay, perfect, thank you. Okay, so now the top will be sine squared of 2x. The bottom will be sine squared of 3x, 1 plus cos 2x. Any questions until here? Okay, so let me continue. So now, the cos of 2x here, this is going to be 1, right? Cos of 0 is 1, and 1 plus 1 is 2. So this term here will approach 2. So this one is not very interesting for me. These are the interesting one because these ones go to 0. 0 over 0. And so this is, I'm going to do as usual, I'm going to divide by x2 top and bottom. Okay, just like we did in the example before. Okay, so I'm going to divide the top by x2 and I'm going to divide the bottom by x2. So I get limit as x approaches 0. So sine squared of 2x over x2 divided by sine squared of 3x over x2 times 1 plus cos of 2x. Okay, you good? Okay, so I have a few questions on the chat. I'm going to answer them in a minute. Okay, let me just finish it. Okay, and then I'm going to put power 2, okay? So equals, on the bottom here, I have the limit as x approaches 0. So here I have sine 2x over x, all this power 2, okay? So I did not change anything. And on the bottom as well, limit x approaches 0, sine 3x over x power 2, and then this one, well, this is also limit x approaches 0 of 1 plus cos 2x, okay? That's right. Okay, so I could put the limit in every term. So now we multiply here by 3, and the top by 3, it's going to pull outside, it's going to become 9, right? Good, like we did before. And this by 2 on top, outside becomes 4. Okay, so now this is 1, this is 1, and this is 2. And then I'm done. So I have 4 over 9 times 2, so 4 over 18. So my answer will be 2 over 9. Okay, so some of you got it right. Okay. No more questions? Okay, let's go one last one. Okay. So that was example 3, I think. So let's do example 4. So show that the limit as x approaches 0 of 1 minus cos x over x is equal to 0. Okay, so this is the second formula that I told you. So now I want you to show it yourselves. Okay, so now you're capable of doing it based on what we did so far. So equals limit x approaches 0, 1 minus cos x over x. So of course, first thing we do, plug in 0, I get 0 on top and 0 on the bottom. Okay. Limit x approaches 0, 1 minus cos x over x. So what do? Multiply by what? Just like before, 1 plus cos x, top and bottom. Okay? Let's go. What do we have on top? Limit x approaches 0, so 1 plus cos x minus cos x minus cos squared x. And on the bottom I have x times 1 plus cos x. Cos x are out. So on top, I'm left with 1 minus cos squared, which is sine squared. Good? Okay, and now I want to separate to recognize the forms that I know. Okay, so I'm going to put limit x approaches 0, so sine squared x is sine x times sine x. So I'm going to write like this. Sine x times sine x, And then the bottom, I'm going to put over x, and here I'm going to put 1 over 1 plus cos x. Okay. I didn't change anything. Okay. The top you multiply, you get sine squared. The bottom you multiply, you get x times 1 plus cos x. And then I'm going to do, why did I do this? Because I recognize that this is 1 now. Okay. So I will separate the limit. X approaches 0 of sine x over x times limit x approaches 0 of sine x times limit x approaches 0, 1 over 1 plus cos x. 3 limits. This is 1. This is 0. And this is 1/2. Okay, so the answer will be 1 times 0 times 1/2, so it's 0. And this is why, that's how I proved that the limit is 0. And we proved the second identity, okay, given that we know this one, right? We know that this is 1.
I have a question.
Sure.
When you do like 1 minus cos 2x, when it turns into sine 2x, is that like an identity we have to know by heart?
1 minus cos 2x, where do you see that?
Like in the third line, and then you turn it into sine 2x.
Oh, so when you say cos 2x means cos squared x, you mean, right?
Yeah, that's what I meant.
Of course, this you have to know. This,
Okay.
I wrote it on the last page again. Okay, so it comes from this one, sine squared x plus cos squared x equals 1. And so sine squared x, if you send the cos on the right side, it's 1 minus cos squared x. Okay?
Okay, thank you.
That's where it came from. Okay? Okay, any questions? That's it for the trig limits. Okay, maybe one or two just for you to get to make sure that you understand the squeeze theorem, because we didn't do enough of these, or maybe 1 or 2 of these. Okay, so could I change page? Good. Okay. So number 5. Okay, so we just did number 4. That's number 5. So limit as x approaches infinity of sine x over x. Okay, so now I'm not approaching 0 anymore. So I can't say that it's 0 over 0. So that's not going to be 1. Okay, so the bottom is infinity. And the top, I don't know what that is. Sine of infinity, I have no idea what that is. Okay, you with me? Okay, so let's go. Equals. So, well, this is what I'm going to do. I'm going to notice that the sine of x is definitely smaller than 1 and definitely greater or equal than -1. So this you know, right? And the sine could never exceed 1 and could never be less than 1. Okay, sure, good. And now what I'm going to do is I'm going to divide every side by x. Okay, I don't need to change the order of the inequality because x is approaching plus infinity. So I'm assuming x is a big number without exaggerating anything. Okay, I know that x is a very big number, so it's positive. So I don't need to be concerned about changing the signs here. Okay, so I just showed that the sine of x over x is definitely between -1 over x and 1 over x. Okay, so if I take the limit, so I'll do the step, I'll do the next step. So -1 over x less than or equal to sine x over x less than or equal to 1 over x. So if I take the limit as x approaches infinity, this still holds.
I don't really get why you changed the signs.
I didn't change the signs.
Oh, okay.
Okay. Now, when x approaches infinity of -1 over x is what? This we spoke already. A number divided by infinity, this is for sure 0. Okay? Same thing here. 1 divided by infinity is also 0. Okay, so I just showed that the limit that I'm looking for is between 0 and 0. So it has to be 0. There you go. What do we call what I just used? Forgot?
Squeeze theory.
Okay, so this is from the squeeze theory. There you go. Okay, so anytime you have a number over infinity, it's going to be 0. And if you have a number that you don't know, for example, it's between something and something, for example, sine or cosine, which are both between -1 and 1, then you would have to use the squeeze theorem like I just did here. Okay, good.
In the result, you write the limit as x approaches 0.
Oh, sorry, no. It's as infinity, and here also. I'm just used to it, even here, sorry. 100%. You're right, it's infinity. Thank you. Okay, good. If we're good, I'm gonna go to continuity right now. Okay, no questions, so let's go. Okay, so we've done limits, continuity, but of course, for continuity, we're gonna need limits as well. Okay, so continuity. So let me give you the definition. The function f is continuous at a certain value x equals a if two things. First of all, the limit as x approaches a of that function has to exist. And second, the limit as x approaches a of f of x is equal to f of a. So this is the definition of a function that is continuous at a certain value. Okay? So this is the definition of continuous at x equals a. So, and a function f is just continuous, not only at a. Okay, so this is continuous at a. So it's just continuous if it is continuous at every value of x. Okay, so if it's continuous for every value, then we say that it's continuous. Okay, so x, let's take this in R. Okay. You've seen this way of writing? Okay, so x in R means in every real number. Let me explain this through pictures. So let me see, how low can I go? That's good. So this. Okay, so I'm just going to represent 4 situations here. Okay. Okay, so we did a bit of continuity a few classes ago. Okay, you just didn't know it because I didn't give you the definition. You will see. It's the first case. So in all cases here, this value here is A, okay, A. And I'm going to draw a function now for each case. Okay, so first one, let's say I have a function like this. Second one, let's go like this. Third one, let's say like this. And the third one, let's say like this. Okay, so here are 3 functions. I mean 4 functions. Okay, so for each function, I'm interested in knowing if the function is continuous at x equals a. Okay, so let's start with the first one. So I need to check 2 things. that the limit as x approaches a exists. So does it exist here if x approaches a? You remember this? How do you know if the limit exists?
If the left limit and the right limit are the
Yes.
same.
Very good, very good. So if I approach from the left, I'm approaching this dot here. If I approach from the right, I'm approaching the top dot. So obviously they're not the same place. So limit as x approaches a of f of x here does not exist. So right away, this is a fail. Okay, so this, the first criteria for the function to be continuous at that point, at that value, fails. Okay, because the limit doesn't exist. So I could stop right away. Let's go with the second one. Does the limit exist here? Does it exist?
No.
No, it doesn't matter whether dot is full or not, who cares? It still doesn't exist because from the left and from the right, it is not the same. Okay, so maybe I will show you with a with my little, approach like we did before. So limit from the left, limit from the left, limit from the left, and then limit from the right, limit from the right, and limit from the right. As you see, this value here is not the same as this value here. Okay, so that's why the limit doesn't exist. And the same argument for the second one. Good? No questions? Okay, third one. Does the limit exist here? Does it exist or not?
Yes.
Yeah, okay, left and right approach the same place. So this exists. So this is good for me. Okay, because if you see left, 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 and then right, 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 same place. Okay, and now I have to check if the limit is equal to f of a. So limit x approaches a of f of x, is it equal to f of a? Is it?
No.
No, because right, f of a is up here. Okay, so this here, this is f of a. Okay, so it means it's not equal to f of a, and so this condition fails, right? The second condition fails here. Okay, and of course the last one, limit as x approaches a of f of x exists, you see it, and the limit as x approaches a of f of x is equal to f of a. Both conditions are satisfied. So this function here is continuous and the other three are not. Do you understand this? Are there any questions? We're almost practically done continuity. Okay, that's all there is to say. But I just, there's a few definitions I need to show you, just last ones. And then we'll do examples. No questions? Okay, so let me just give you a definition. So this function here, the last one, is continuous. At x equals 8. Continuous because both conditions are satisfied. These three are discontinuous, okay? Except that there is a name for the type of discontinuity, okay? So these two here, the first two are different because the function jumps. At A, it has a jump, okay? So we call these, this and this, a jump discontinuity. So I'm gonna write this down. Jump discontinuity at x equals A, and same here, jump discontinuity at x equals A. Okay, these two, they have jumps. This is not a jump. The function does not jump. It's just one point that spoils everything for me there. Okay, so this is called a removable discontinuity at x equals A. Okay, so two words, two new words, jump discontinuity, removable discontinuity. Okay, two types of discontinuity. Any questions? That's all there is to say on continuity. That's all. Okay, for this course. Okay, I'm going to give you some examples. Okay, which are not, they're really not difficult. You'll see. Okay, and then I'm going to post a worksheet on continuity. Okay, so you should, after the examples we do today, you should be able to complete the web work. Okay, without any trouble. Okay, have you advanced? Did you do the limit questions?
Yes.
Okay, it's okay. It's okay. You're surviving. I guess so. Okay, so here's a few examples. So, example, let's me create a function, f of x equals 2. So x squared minus 9 over x minus 3 if x is smaller than 3. Okay. Let's say 9 if x is equal to 3. And let's say sine of 6x minus 18 over x minus 3 if x is greater than 3. So here, I just invented it right now, okay? So here's a function, a piecewise function, okay? And the question is f continuous at x equals 3, okay? And if it is not continuous, classify the type of discontinuity. Okay, so basically here I'm asking if it's not continuous, tell me if it's a jump or a removable discontinuity. Okay. Okay, so Zach, you already put an answer. That was fast. I mean, I don't know how to do this. I think it's wrong. Your answer is wrong, but I didn't do it yet. Okay, you went really fast. Okay, so do you want to try it or you want me to do the first one? No answer?
Could you show us the first one?
So I'm going to show you the first one, okay? So let's go. So obviously, I'm interested in at 3, at x equals 3, which is normal because this is where the functions, right? There's a connection at 3. Before 3, it's this function. After 3, it's this function. And at 3, the function is 9. So I want to see if everything is nice and smooth, or if there's a jump, or if there's a hole, or I don't know. Okay, we'll see. Okay, so for this, we have to do the limit from the left and limit from the right, right, to see if it exists first, and then find if it's equal to the value of the function, basically if it's equal to 9. Okay, you with me? So let's see limit as x approaches 3 from the left of f of x equals what? Okay, so if I'm to the left of 3, so this is the function in effect. When x is less than 3, this is the function in effect. So I want to write limit as x approaches 3 from the left, x2 minus 9 over x minus 3. So I have to evaluate this limit. Okay, and so the first thing I do, of course, I plug in the 3 and see. 3 squared is 9 minus 9 is 0 over 0. So I have 0 over 0 here, this undetermined form. And so I'm going to do a bit of algebra here, which is easy in this case, which is just a factor. Okay, so I have x minus 3 times x plus 3 divided by x minus 3. And so I could cross out the x minus 3's. And so now I plug in 3, I get 6. We're good? Any questions? So as x approaches 3 from the left, the function approaches 6. Okay, let's do from the right now. So limit as x approaches 3 from the right of f of x will be limit x approaches 3 from the right. So the function that's in effect when x is bigger than 3 is this one. So sine of, so this I could factor, actually, I could factor out a 6, right? I could factor out a 6. So 6 times x minus 3 over x minus 3. Is that okay? Okay, so this is the sine of all this. So again, I plug in 3 inside, I get sine of 0 over 0. So let's do. So remember, we just did function limits involving sines. So I need this, what's inside the sine, what's on the bottom to be the same. So what am I going to do? I will multiply by 6 on top. Okay? And now I have 6 times limit as x approaches 3 from the right of sine of so 6x minus 18 over 6x minus 18, and this is 1. Okay, this now is 1 because I have sine of 0 over 0 and they're both the same. Okay, and so my answer is 6. Oh, this looks pretty nice. Okay, so the only thing I need to check now is, so I know, so therefore, the limit as x approaches 3 of f of x is equal to 6, right? Because left and right are the same. Okay, but unfortunately, limit x approaches 3 of f of x equals to 6 is not equal to f of 3, which is 9, right? F of 3 is 9. So it is not continuous. You understand? So the limit exists, but it's not equal to f of 3. F of 3. So what do we have here? Continuous or not?
Not continuous.
Sorry?
It's not continuous because it's not the same.
Perfect. And what type of discontinuity is it?
Removable discontinuity.
Removable. Perfect. So since the limit as x approaches 3 of f of x exists, but the limit as x approaches 3 of f of x is not equal to f of 3, then f has a removable discontinuity at x equals 3. Okay, so this sentence is important because that's where you write, oops, I'm walking up a bit. That's because that's where you explain your answer. Okay, so it's not a jump discontinuity, it's a removable discontinuity. Okay, if instead of being a 9 here, this would have been a 6, then it would have been continuous. We're good? You get it? Okay, let me just have a little space in the paper, so I will just maybe try to represent the graph of this. Okay, so everything is happening at x equals 3. Okay, so let's say this is 3 here. Okay, so on the left, function goes a bit like this. Okay, then it's approaching six. On the right, it's approaching 6 also. Okay, apparently. I don't know how it looks like. Who cares? Okay. And at 3, the function is worth 9. Okay, you get it? So I see there's a jump. Not a jump, sorry, a removable discontinuity.
I have a question.
Sure.
Is it compulsory to draw the graph?
No, it's not compulsory for now, but because as you see, I didn't draw this. This is just to explain to you. Okay, so I drew anything here, but at the end of the course, you will see that I'm going to ask you to draw exactly a graph, perfect, precise, complicated graphs. Okay, but we'll get there.
Okay.
Okay, one thing at a time. Any questions? Okay, so let's do one more example for continuity, and then that's it. We're done continuity, and we're ready to go to derivatives to our next class. So I wanted to finish continuity today, and I'm happy I'm doing this. Okay, so let's do one last question. Number example here. Okay, so it's a question from the worksheet. that I'm going to post right after. Okay, so find the values of C and K that make f of x continuous on minus infinity to plus infinity. Okay, so I don't need to add this. When I say continuous, it means from minus infinity to infinity. Okay, so I'm going to give you the function. So f of x is equal to, so x plus 2c if x is less than -2, then 3cx plus k if x is between -2 and 1, and 3x minus 2k if x is greater or equal than 1. Oops, sorry, there's an equal here and there's no equal here. Okay, so the or equal is here. Okay, so here's a function that's defined, it's piecewise, and it's defined 3 pieces. Okay, so I want it to be continuous everywhere. In other words, I need to find C and K, these called parameters, that would make this function continuous. In other words, I want it to connect correctly at -2. So these two have to connect nicely. And at 1 also, these two have to connect nicely. Okay, you understand the question? Okay, so we have about 5 minutes left. So I'm going to do it, okay? And you'll have time to practice with the worksheet, okay? Or you could review the video if it's still not clear, okay? So let's see at x equals -2. Let's start with this, okay? So it has to be continuous at -2. So in other words, limit from the left equals limit from the right equals f of -2. So let's go. Limit as x approaches to -2 from the left of f of x equals the limit as x approaches -2 from the left. So which function am I going to use if I'm at the left of -2?
The first one?
The first one, because I'm on the left of -2. So I'm going to use x plus 2c equals, so I just plug in -2 in the x. So I get -2 plus 2c. This is what my limit is. Okay, good. And from the right, limit x approaches -2 from the right of f of x equals limit x approaches -2 from the right. Which function do I use if I'm on the right of -2?
The last one?
No, the last one, I'm on the right of 1. I'm really far. If I want to be to the right of -2, so right between -2 and 1, this is the function. So I have to use the second one. Okay, this function doesn't get close to -2. It starts at 1. Okay, so 3cx plus k, and then you plug in -2 in the x, so I get -6c plus k. Are we good? And f of -2, f of -2 is what? What's f of -2? Okay, what is the value of the function when x is minus 2? Okay, so when x is minus 2 equal to, so this is the function, so it's worth negative 6c plus k. Okay, so the function is continuous at minus 2 if all these three values are the same. Okay, so I'm gonna write this down. Maybe like this. So f is continuous at x equals minus 2 if, well, they're all equal. So basically, if negative 2 plus 2c equals negative 6c plus k. Okay, and I will send everything on the left side. So I will get 8c minus k is equal to 2. So this is one little equation that I have here. Okay, so for the function to be continuous at minus 2, this relation between c and k needs to be satisfied. Questions? Let's do the same thing now at x equals 1, at the other connection. So again, limit x approaches 1 from the left of f of x equals, and then limit as x equals 1 from the right of f of x equals. And of course, f of 1 equals. Let's try all these, all three. Okay, so if I approach x to 1 from the left, which function do I use?
The second function.
The second one, very good. So 3cx plus k, plug in 1 in the x, I get 3c plus k. And 1 from the right, of course, I'm going to use the last function. So 3x minus 2k. And so I get 3 minus 2k when I plug in x equals 1. Okay, and f of 1, which function do I use to find f of 1?
The second one?
The second one, because equals, that's when it's equal to 1, is this function. Very nice. So I get 3c plus k. And again, these three values need to be equals to each other. Okay, so I'm going to write f is continuous at x equals 1 if, so these three values are the same, so basically 3c plus k is equal to 3 minus 2k. Okay, so I'm going to send the k's on the left, so I get 3c plus 3k equals 3. I could divide everything by 3, so c plus k equals 1. Here's my second equation. Okay, so how do I solve this? I have to do a system of equations, okay, like you did in high school. Okay, so I'm gonna write this down. So f is continuous. Okay, so on minus infinity to infinity. If, well, these two equations are satisfied. Okay, so basically c plus k equals 1, and then 8c minus k equals 2. This is my system. You know how to solve this? I guess you do. So I think I would just add the two equations. If you add the two equations, the k's will cancel. So I'm going to get 9c equals 3, which means that c equals to 1/3. And if c equals to 1/3, I plug it in here, I get k equals to 2/3. There you go. These are my values that would make my function continuous everywhere.